So linear inequalities. If you know how to solve a linear equation, you already know how to solve a linear inequality. There's one minor thing we have to watch out for. So here I have a linear equation, I've got an equal sign, and next to it I have a linear inequality that looks basically the same, except where I have my equal sign, I have a greater than or equal to symbol. We know how to solve this. First thing you want to do is subtract 5 on this side so that it's gone from the left-hand side. Once that's simplified, we just divide both sides by 3 to get our final answer. I did the exact same thing here. To isolate for x, I have to bring that 5 over and subtract, get -9, and divide both sides by 3, and get x is greater than or equal to -3. So that says that so long as x is greater than or equal to -3, this inequality holds. This left-hand side will always be greater than or equal to -4. There's one minor thing you have to watch out for. We treat inequalities like equations, except if we divide both sides of the inequality by a negative number, or multiply both sides of an inequality by a negative number, the inequality symbol will swap directions. So here I have a greater than or equal to symbol. I want to get rid of this -7, and so I add it on the right-hand side, and now I have 12. Now I want to get rid of this -2, and the opposite of multiplying by -2 is, of course, dividing by -2. And because I'm dividing by a negative, from this step to this step, I've swapped the inequality symbol from a greater than or equal to a less than or equal to. So one small thing to look out for, otherwise treat it exactly like you would an equation. When we're dealing with inequalities, it's possible to get a double inequality. We can get some value of x between two values. Of course, that doesn't work for an equation. X can only be equal to one single thing at a time. But with inequalities, x can be in some range. So here I have -7 is less than -2x plus 1, which is less than -3. You can think of this as having 3 sections, and my goal is to get x alone in the middle. So if I want to get x alone, first thing I want to do is get rid of that plus 1, just like you would in an equation. We know that the opposite of adding 1 is subtracting 1. If I subtract 1 from each of my 3 sections, I'm left with -7 minus 1. Now it's gone from the middle section, and -3 minus 1. Now I've simplified. That becomes -8. That becomes -4. And once again, if I want to get rid of this -2 in front of the x, I've got to divide each of the sections by -2. And don't forget, because I'm dividing by a negative, the inequality symbols will swap direction, and we get this as our final answer. X is some number between 2 and 4. That says that as long as x is some number between 2 and 4, this initial inequality will hold. So for polynomial inequalities, unfortunately, it's not so straightforward. The easiest way to deal with a polynomial inequality is to think of it graphically. So say this is some function f of x, and I ask you, when is f of x greater than 0? That's another way of saying, when are your y values greater than 0? When is the graph in the positives? So if I look at this graph, in this entire section here, between 1 and 2, my graph is above the x-axis, which means my y-coordinates are positive. So we have one interval. F of x is greater than 0, or is positive, when x is between -1 and 2. Then my graph becomes negative for a bit, but after 3, it'll be positive again, on toward infinity. So we have another interval where f of x is positive when x is greater than 3. Alternately, if you're asked when is f of x negative or when is f of x less than 0, we're looking at the intervals on this graph when it's below the x-axis. So over here, when x is less than -1, that entire section, your graph will be below the x-axis. And in here, in this little bit, between 2 and 3, your graph is negative or or below the x-axis. So here's an algebraic solution. So say you factored this, and you got these 3 factors. If we were to solve, we know that the solutions to this are +4, -1, +3. So those are the zeros on my graph. -1, +3, and +4. Remember that this means that that is an order 2 0, so my graph is going to bounce at 3. And because of the negative in front, my graph is flipped over, and so the end behavior is pointing downward because this is an even degree polynomial, degree 4. So there's my end behavior, there are my zeros, there's the special 0 that bounces back. I have to figure out when this polynomial is less than or equal to 0. Well, when is it below the x-axis? Right here, when x is less than -1, and over here, when x is greater than 4. But you'll notice I also included the 0, 3. Because it has the equality symbol under here, you have to make sure to also include all of the zeros. So my final answer, when x is less than or equal to -1 in order to include the 0, when x is equal to 3 to include the 0, and finally when x is greater than or equal to 4, and again include the 0. Unfortunately, rational inequalities are a lot more complicated. If you remember way back when we did linear inequalities, the rule was if you multiply or divide both sides by a negative value, the inequality symbol flips. When we're dealing with unknowns, we can't just multiply both sides because we don't know when it's positive and when it's negative. We don't know whether we should swap the inequality symbol. So for that reason, the best we can do is simplify this. I'm going to bring this rational over to the left-hand side. Now, in order to bring these two fractions together, I need a common denominator. These two multiplied together. So if I want to multiply this over here, I've also got to multiply the numerator. So there it is. I've taken that rational, multiplied top and bottom by x minus 3. Same over here. If I want this over there, I've got to multiply top and bottom by x plus 1. Now that I have a common denominator, I can subtract the numerators, this, subtract this, distribute everything out, collect like terms. If you do that, the numerator simplifies simply to x minus 7. So now this problem simplifies to when is this rational function greater than or equal to 0? When is it positive and when does it equal 0? The equality part is pretty easy to answer. At 7, when I put 7 up here, 7 minus 7 is 0, and over whatever the denominator may be is still 0. But when is it positive? When is it greater than 0? You have two options. Just like with polynomial inequalities, we sketched the graph to figure out when it's above the x-axis and when it's below the x-axis. You could sketch it. Alternately, you can make a sign chart. This graph, if we were to graph it, has an x-intercept at 7, and vertical asymptotes at -1 and +3, the values that make the denominator 0. The only way a function can swap from being positive to negative or negative to positive is if it passes through a 0 or it sort of hops over the asymptote. On one side of the asymptote, it's positive, and then on the other side of the asymptote, it may be negative. So we're going to test when this function is positive and when this function is negative using the 0 and the 2 values for the vertical asymptotes. So I've made this chart with 4 intervals before my first vertical asymptote, between my vertical asymptotes, between a vertical asymptote and 0, and finally after my 0. Those are all the spots where it can swap from positive to negative and negative to positive. To simplify this, I've put each of the factors here. Now I want to figure out when x is less than -1, are each of these factors positive or negative? Well, we can just select a number, say -2. If I put -2 into each of these, this would be -9, so it's negative. We don't actually care about the value, just whether it's positive or negative. If I put -2 in here, it would also be negative, -1. And if I put -2 in here, it would be -5. So all 3 of the factors would be negative, and therefore when I multiply these and divide this by that, you would get some negative number, regardless of which value of x you chose. Next, we want to test some value between -1 and 3. 0 is very easy. If I put 0 in here, that will be negative. 0 in for x here, that will be positive, +1. 0 in for x here, that will be -3. A negative divided by a positive and a negative multiplied ends up in a positive, right? This would be a negative over a negative. Moving on to some value between 3 and 7, say 4. This would be -3. This would be positive, and that would also be positive. Once again, this is the numerator. You divide it by the denominator. If you did so, the final answer would be negative. And finally, the last interval, some number greater than 7, 8, positive, positive, 8 minus 3, +5. All of these would be positive if we selected some value greater than 7. Multiplying these, dividing these, the final answer would be positive. So back to the question, which was, when is this function greater than or equal to 0? Well, greater than 0 means positive. So right here and right here, those are two intervals where it's positive. And so my final answer is, as long as x is between -1 and 3, and x is greater than or equal to 7. Remember we said the 0 is also a solution because we also want to know when it's equal to 0.